Welcome, curious minds, to the deep dive. Today, we're embarking on a journey into a world you absolutely cannot see with your naked eye, yet it's quietly revolutionizing everything around us.
Mhm.
From how we treat diseases to the very phones in our pockets, it's all being shaped by the tiniest building blocks imaginable.
That's right.
We are, of course, diving deep into the fascinating realm of nanotechnology and nanoscience.
It's truly a field that sounds like something out of science fiction, but it's very much grounded in the present, profoundly impacting our daily lives and holding immense promise for the future.
Our mission for this deep dive is to unravel the core concepts of this domain, explore the astounding properties materials take on at this incredibly small scale, and delve into their widespread applications across industries.
Yeah, everything from medicine to electronics.
Exactly. Medicine, electronics, energy, even environmental cleanup. But we'll also examine the important considerations that come with such powerful technology. Our goal is to provide you with a thorough, yet engaging understanding, transforming complex ideas into clear, memorable insights.
Hopefully, yeah.
So let's start with the fundamental question. What exactly is nano?
Okay, well, at its core, nanoscience is the study of materials and phenomena at the nanoscale. We're talking about incredibly small dimensions.
Right.
This research helps us understand how things behave when they're truly tiny. For example, this understanding is already being used to purify groundwater fouled by solvents, metals, and petroleum across numerous sites.
And when we say tiny, we mean tiny.
We really do.
To give you a sense of scale, atoms are just a few tenths of a nanometer in diameter. Typical particles we study are usually just a few nanometers in size.
That's where nanotechnology comes in. It's often defined as the design of functional systems at the small scale. Now, this broad definition covers a lot of the work happening today, as well as more advanced sort of theoretical concepts.
Okay.
However, it's worth noting that the original vision for nanotechnology, the authentic sense, if you like, was about the precise ability to construct items from the bottom up.
Atom by atom.
Exactly, atom by atom, with tools and processes being developed right now. A lot of what we call nanotechnology today, while working at the nanoscale, might not fit that strict atom-by-atom assembly definition, you know?
That distinction is important. This incredibly precise building capability was first dreamed up way back in 1959 by the brilliant physicist Richard Feynman.
Ah, yes, Feynman.
He gave a now famous lecture titled "There's Plenty of Room at the Bottom," essentially laying the theoretical groundwork for what we now know as nanotechnology. He truly saw the potential.
He absolutely did. To put a nanoscale into even more perspective, the term nano itself means 1/billionth.
1/billionth.
Yeah, or 10 to the power of -9. 10 to 9. To visualize this, consider that a single human hair is about 80,000 nanometers wide.
Oh.
A nanometer is roughly the thickness of a strand of DNA. It's almost unimaginably small.
And so, in essence, if you're designing, constructing, or even just using systems that operate at less than 100 nanometers, you're interacting with nanotechnology.
Pretty much, yeah.
This means that some forms of nanotech have actually been around for centuries, long before we had the word for it.
That's a great point.
Think about the vibrant, deep colors in medieval stained glass windows. Those striking hues aren't just dye. They result from nanocrystals that formed within the glass during the heating and cooling process.
Exactly. Those artisans were nanotechnologists without knowing it.
It just goes to show, at this scale, size truly matters.
Absolutely. That's a key principle. At the nanoscale, materials take on properties that are radically different from larger chunks of the exact same substance.
How so?
Well, for example, their color can change dramatically. Their transparency can fluctuate. Even their melting point can be significantly altered. These aren't minor tweaks. They're fundamental shifts in how the material behaves.
So what's the underlying theory behind all of this? Nanotechnology isn't just a collection of random discoveries, right?
Yeah.
It's built on something more solid.
Definitely. It's built on a cohesive, unified theoretical framework. It serves as a guide for advanced students and professionals in various scientific fields, from engineering to organic and physical sciences, people who already have some grounding in, say, quantum and statistical mechanics.
Okay.
It also provides an essential overview for experts in related fields who need to grasp the core concepts of nanotechnology. Understand what it's all about.
And I imagine that requires learning a whole new language almost.
You're not wrong. Given nanotechnology's inherently interdisciplinary nature, it necessitates a vast vocabulary. You really need to be familiar with abbreviations, substance formulas, concepts, definitions, equations, and theories from many different scientific domains.
It's truly a convergence of multiple disciplines.
It really is.
And within this broad field, we generally talk about two main approaches, top-down and bottom-up. Can you break those down?
Sure, the top-down approach is kind of what you might think of as traditional manufacturing, just at a very small scale.
Like carving.
Yeah, exactly. It involves techniques like machining and engraving, starting with a larger piece of material and essentially carving it down to the nano size. This was the primary method for 20th century scientists.
Okay, that makes sense. So what's bottom-up?
The bottom-up approach, on the other hand, is closer to Feynman's original vision. It involves assembling nanostructures from individual atoms and molecules, building them up piece by piece.
Like tiny Legos?
Sort of, yeah. This is where the precise control over material and organic properties truly shines. Ultimately, nanotechnology is about applying established scientific principles to the nanoscale, constantly pushing the boundaries of miniaturization.
Looking back at the history, while nanotechnology feels like a very modern field, the core concepts and initial experimental work actually developed over a longer period, really expanding in technical research relatively recently. Is that right?
That's exactly right. The field really started to take shape in the 1980s.
What happened then?
Well, this was thanks to major experimental advances, the invention of the scanning tunneling microscope, or STM, in 1981.
The one that lets you see atoms.
Pretty much, yeah. And the discovery of fullerenes, those incredible soccer ball-shaped carbon molecules, in 1985. These breakthroughs coincided with the popularization of a theoretical framework for nanotechnology, especially with the 1986 publication of the book Engines of Creation.
Ah, Drexler's book. That made waves.
It certainly did.
So by the early 2000s, public awareness of nanotechnology was rapidly increasing, and with it came debates.
Yeah. There were discussions about the potential implications of the technology, as well as the feasibility of the more ambitious applications envisioned by proponents of molecular nanotechnology.
Right, the self-replicating nanobots kind of stuff.
Exactly. Around this time, governments worldwide also began to actively encourage and fund research in this burgeoning field.
Despite those early debates and the theoretical nature of some of the work, the early 2000s also saw the first viable applications of nanotechnology emerge, didn't they?
They did. However, these were primarily what we call bulk applications of nanomaterials. Think about adding nanoparticles to existing materials to enhance their properties.
Like making plastic stronger or something.
Precisely. Rather than the more radical, transformative visions that many had for the field, we were really just scratching the surface of what was possible back then.
So let's step back and consider the broader picture of nanotechnology's impacts. What are some of the truly significant benefits we're seeing or expecting from this field?
Oh, the potential benefits are incredibly broad, impacting nearly every aspect of our lives. We're looking at improved manufacturing methods, more effective water purification systems, advanced energy solutions, physical enhancements to materials, breakthroughs in nanomedicine.
The list goes on.
It really does. Better food production methods and nutrition. Imagine large-scale infrastructure that can practically self-assemble or repair. The possibilities are vast.
And it's not just what it can do, but how. Because nanotechnology operates at such a compact size, it can potentially automate everyday tasks that were previously impossible due to physical limitations.
Exactly. This could lead to a significant reduction in labor, land usage, or even, human protection needs in various industries. Think about processes requiring minimal human intervention, operating at scales we once only dreamed of.
But as with any powerful technology, we must also consider the potential risks.
Always. These include environmental, health, and security concerns. There are also property-related issues, such as the potential disruption of traditional industries as nanotech-enhanced goods become dominant.
And privacy.
Privacy advocates have also raised concerns, absolutely. It's crucial that we carefully monitor and understand any potential negative properties of nanoparticles, especially if they are underestimated or overlooked.
That's a critical point. The question of whether nanotechnology requires special oversight and regulation is a really controversial one.
It is. Regulatory bodies like the United States Environmental Protection Agency, the EPA, and the European Commission's Health and Consumer Protection Directorate are already working to address the potential risks of nanoparticles.
That's good.
And interestingly, the organic food industry has been quite proactive. They've led the way by excluding engineered nanoparticles from formal organic produce. This started in places like Australia and the UK, and more recently in Canada, and it's also part of the Demeter International Standard for Organic Food.
So So beyond just the direct toxicity risks, there are broader societal challenges that come with nanotechnology.
hmm Many experts suggest that these societal issues shouldn't just be seen as sort of downstream risks to be managed after the fact.
What do they mean?
Instead, they argue that these challenges need to be factored into upstream research and development right from the beginning to ensure that technological progress truly aligns with common societal goals. Build it in from the start.
Makes sense. Let's delve a bit deeper into the conceptual side, looking at how materials behave at the nanoscale from a macro to nano perspective.
Okay, well, you find that numerous phenomena become much more pronounced as the size of the system shrinks. This includes what we call statistical mechanical effects, and even more dramatically, quantum mechanical effects.
Quantum effects, like weird physics?
Kind of, yeah. For example, the quantum confinement effect can significantly alter the electronic properties of solids when particle size decreases. Things just don't behave the way you expect them to based on the bulk material.
It's interesting to note that these quantum effects aren't really significant when you move from the everyday world to micro dimensions.
Hmm.
But when you reach the nanometer size range, typically 100 nanometers or less, they become absolutely critical.
That's right. This is what we call the quantum domain.
So it's a whole new ballgame down there.
Pretty much. In addition to quantum effects, many physical properties like mechanical strength, electrical conductivity, and optical behavior can differ significantly from their macroscopic counterparts.
Like the stained glass example.
Exactly. For instance, the dramatic increase in surface area to volume ratio at the nanoscale profoundly changes a material's mechanical, thermal, and catalytic properties. Fields like nanoonics, which explores ion movement and reactions at the nanoscale, and nanomechanics, focusing on the mechanical properties of nanosystems, are becoming increasingly vital.
But potential risks, too.
Yes, we also need to be mindful that the catalytic activity of nanomaterials could pose risks when interacting with biological systems. That enhanced reactivity cuts both ways.
Now let's switch gears to a simple to complex, or molecular perspective. Modern synthetic chemistry has become incredibly sophisticated. We can now design and create miniature molecules with almost any desired structure, right?
Absolutely. These methods are widely used to produce a vast array of useful chemicals, from pharmaceuticals to industrial polymers. It's really quite amazing what chemists can build molecule by molecule now.
So this incredible ability leads to the next challenge, extending this level of control to larger assemblies.
Exactly. The goal is to develop methods to precisely arrange individual molecules into supramolecular structures in a highly ordered, functional way.
How does that work?
This relies heavily on concepts like molecular self-assembly and supramolecular chemistry, where molecules are designed to spontaneously arrange themselves into complex, functional structures through a bottom-up approach. They basically build themselves.
A key aspect here is the concept of molecular recognition. Is that like molecules knowing where to go?
In a way, yes. Molecules can be designed so that a specific arrangement is favored due to subtle, non-covalent interactions between them, weak forces, like tiny magnets.
Ah,
Think about how DNA strands perfectly pair up based on Watson-Crick rules.
up pairs with T, G with C.
Right, or the incredible specificity of an enzyme targeting only a single substrate, or even the precise folding of a protein. It's all about how these tiny components intrinsically interact and attract each other to form something much more complex and valuable.
This brings us to a long-standing vision within the field, often called molecular nanotechnology or molecular mechanosynthesis.
Right. This refers to engineered nanosystems, essentially nanoscale machines, that operate at the molecular level. Molecular nanotechnology is closely associated with the idea of a molecular assembler, a theoretical device that could build a desired structure or device atom by atom using precise mechanosynthesis.
That sounds very sci-fi again, like those nanobots.
It has that feel, definitely. It's important to differentiate this from more common bulk nanotechnology, which often involves creating materials like carbon nanotubes or nanoparticles on a larger scale.
Okay.
When Eric Drexler popularized the term nanotechnology, he was referring specifically to the potential for advanced machinery based on these molecular-level construction systems, drawing inspiration from how biological systems work.
Like how our cells build proteins.
Exactly. The foundational idea was that if natural biological systems could create sophisticated, stochastically optimized molecular machines, then it should be possible for us to engineer complex molecular machines as well. This concept spurred much of the early theoretical work.
So let's take a broader view again and discuss the overall impact of nanotechnology across society. What are the key areas where we're seeing its influence?
Well, first, the reach of nanotechnology is incredibly wide. It's spanning remedial, industrial, psychological, legal, and environmental applications. It extends across manufacturing, natural science, chemistry, computing, material science, and communications. It's truly
Okay,
pervasive.
so it's everywhere. Second,
Second, the most significant benefits include enhanced manufacturing processes, more effective water purification, advanced energy systems, physical improvements to materials, breakthroughs in nanomedicine, better food production and nutrition, and revolutionary advancements in communication and infrastructure. The sheer diversity of benefits is astounding. Third, because nanotechnology operates at such a compact size, it has the potential to automate tasks that were previously impossible due to physical limitations. This could significantly reduce requirements for labor, land, or even human presence, potentially leading to more efficient and less resource-intensive processes.
and fourth, the risks we touched on.
And fourth, as we discussed, there are impending risks. These include environmental and health concerns, as well as the potential displacement of traditional industries as nanotech-enabled products become dominant. Privacy advocates also raise important concerns. These negative effects, especially if overlooked, could be quite significant.
And the regulatory side is still evolving.
Right. On the regulatory front, there's ongoing debate about whether nanotechnology requires special oversight. Regulatory bodies like the US EPA and the European Commission are already working to address potential nanoparticle risks. And as we mentioned, the organic food industry has been a leader in excluding engineered nanoparticles from certified organic produce.
And it's not just about whether they're toxic.
No, exactly. Beyond just the direct toxicity risks associated with early generation nanomaterials, nanotechnology also brings broader societal challenges. Many experts suggest that these community issues need to be understood and addressed, not just as after-the-fact risks, but integrated into upstream research and management. This ensures that the advancement of knowledge truly serves common objectives.
Okay, let's get more specific about types of impact, starting with health. This refers to the potential effects of nanotechnological materials and procedures on individual health. As nanotechnology is still an evolving field, there's considerable discussion about its potential to improve health versus the risks it might pose.
That's the core tension, yes. We can essentially split these health impacts into two areas. The potential for nanotechnology to offer therapeutic applications for treating disease,
They're good stuff.
and the potential health hazards from exposure to nanomaterials. Let's start with the exciting medical side. Nanomedicine is, quite simply, the therapeutic application of nanotechnology. Approaches range from using nanomaterials for treatment to nanoelectronics biosensors, and even the visionary future applications of molecular nanotechnology, like tiny biological machines.
Like cell repair bots.
Potentially, way down the line, the aim of nanomedicine right now is to deliver a valuable suite of research tools and clinically useful devices in the near future.
And the National Nanotechnology Program envisions new commercial applications in the pharmaceutical industry.
Yes, including sophisticated drug delivery systems, novel therapies, and in vivo imaging, meaning imaging inside the body. Research is also actively pursuing neuron-electronic interfaces and other nanoelectronics-based sensors.
Looking further ahead, the exploratory field of molecular nanotechnology suggests that microscopic cell repair apparatus could truly revolutionize medicine. Is this getting much funding?
It is. Nanomedicine research is well-funded. For instance, the U.S. National Institutes of Health funded a 5-year plan back in 2005 to establish 4 nanomedicine centers, and that support continues.
And is it reaching the market?
It is. By April 2006, the journal Nature Materials reported that 130 nanotech-based drugs and delivery systems were in development worldwide. Nanomedicine is a substantial industry, with sales reaching $6.8 billion in 2004. With over 200 companies and 38 products globally back then, at least $3.8 billion is invested in nanotechnology R&D annually, and those numbers have only grown.
So it's having a real economic impact.
Definitely. As the nanomedicine industry continues to grow, it's expected to have a significant impact on healthcare and the economy. Sales hit $16 million in 2015, and R&D investment keeps climbing.
Okay, now for the other side, health hazards, the domain of nanotoxicology.
Right. This field studies the potential health risks of nanomaterials. Because of their incredibly tiny size, nanomaterials can be much more easily absorbed by the human body than larger particles.
That makes intuitive sense. Smaller things get in easier.
Exactly. A critical question is how these nanoparticles behave once inside the body. Their behavior is influenced by their size, shape, and how reactive their surface is with surrounding tissues. A concern is what happens if non-degradable or slowly degradable nanoparticles accumulate in organs
What?
and how they might interact with natural biological processes within the body. It's complex.
And they interact differently because they're so small.
Yes, due to their large surface area, nanoparticles, when exposed to tissue and water, will immediately absorb various macromolecules onto their surface. This coating can change how they interact with cells.
So it's hard to predict.
It's very difficult to generalize about the health risks. The sheer number of different materials and potential toxicities means each new nanomaterial must be assessed individually, considering all its properties. You can't just say nanoparticles are safe or nanoparticles are dangerous.
Got it. Moving on to environmental impact. This refers to the potential effects of nanotechnological equipment and strategies on the environment. Again, I imagine there's debate here.
Absolutely. As this is a developing field, there's significant debate about the extent to which industrial use of nanomaterials will affect organisms and ecosystems.
But there's a positive side, too. Green nanotechnology.
Yes, green nanotechnology aims to use nanotechnology to improve environmental sustainability, both in manufacturing processes and in products. This includes developing environmentally friendly nanoproducts and using nanoproducts to support sustainability efforts, things like better solar cells or water filters.
And the flip side is nanopollution.
Right. Nanopollution is a general term for waste generated by nanodevices or during the industrial production of nanomaterials. This waste primarily refers to particles released into the environment or those that remain embedded in discarded products. Where do they end up? How long do they last? These are big questions.
And again, beyond toxicity, the broader societal challenges.
Exactly. As we've emphasized, beyond the direct toxicity risks to human health and the environment, nanotechnology presents broader societal challenges. Many experts suggest that the societal implications shouldn't just be viewed as downstream risks. Instead, these challenges should be integrated into the earliest stages of research and management to ensure that scientific progress truly serves common societal objectives.
Okay, let's zoom in on the nanomaterials themselves. When we talk about nanomaterials, we're referring to substances that have particles or constituents with at least one external dimension in the size range of about 1 to 100 nanometers.
Is that the standard definition?
That's the generally accepted range, yes. Specifically, nanoparticles are substances where all three external dimensions are at the nanoscale.
And it's crucial to distinguish engineered nanoparticles from naturally occurring ones. Yes, or from byproduct ultrafine particles, like those from welding or diesel engines, which are often physically and chemically quite diverse, sort of a messy mix. Engineered nanoparticles, by contrast, are deliberately designed and manufactured with very precise properties related to their shape, size, surface characteristics, and chemistry.
Okay, so they're tailor-made.
Precisely. These engineered properties are evident whether the materials are in aerosols, colloids, or powders. What's fascinating is that the behavior of nanomaterials often depends more on their surface area than on their elemental composition.
Surface area is the key.
It's huge. This surface area to volume ratio significantly influences their reactivity, capacity, and electrical properties. There's just much more surface available to interact with the surroundings compared to the same amount of bulk material.
And understanding the morphology, the structure and form is important too.
Absolutely. Understanding that structure at the nanoscale is key to creating nanostructure equipment. Much of the progress in this field relies on advanced tools like nanoscale resolution microscopes.
Like that STM we mentioned.
Exactly. Tools like that allow us to quantify and manipulate these ultra-tiny structures. Continued progress also requires consistent resources for nanotechnology research and for scientists to develop skills in new application areas. Support for learning and teaching in nanotechnology, often through research guidance networks, is also vital.
We're seeing a rapid growth in innovative mixture technologies that combine nanotechnology with other fields, right?
Yes, combining it with materials, science, engineering, IT, biotechnology, and green technology. This interdisciplinary progress requires strong networks across various research areas and robust partnerships that transcend traditional scientific boundaries. It's all coming together.
Is there an official definition of nanomaterial?
There is. The European Commission defines a nanomaterial as a natural, incidental, or manufactured material containing particles, either unbound as an aggregate or as an agglomerate, where for 50% or more of the particles in the size distribution, one or more external dimensions are in the 1 millimeter to 100 millimeter range.
That's quite specific and common examples.
Common examples of these engineered nanomaterials include carbon buckyballs, also known as fullerenes,
The soccer balls.
soccer balls, yeah, carbon nanotubes, various metal or metal oxide nanoparticles, and quantum dots. These are the fundamental building blocks of many exciting new technologies.
Can we categorize these nanomaterials?
Broadly, yes. Modern nanomaterials can be categorized into four main types. First, carbon-based materials. These are primarily composed of carbon and typically take the form of spheres, ellipsoids, or tubes.
Fullerenes and nanotubes.
Exactly. The spherical or ellipsoidal ones are called fullerenes, and the cylindrical ones are carbon nanotubes. These materials have immense potential in areas like advanced films and coatings, creating stronger and lighter materials, and various electronic applications.
Okay, type 1, carbon. What's next?
Second, we have metal-based materials. This category includes things like quantum dots, nanogold, nanosilver, and various metal oxides like titanium dioxide.
Tell me more about quantum dots.
A quantum dot, to elaborate, is a tiny semiconductor crystal containing hundreds or thousands of atoms with dimensions ranging from a few nanometers to a few hundred. What's really crucial here is that by simply altering the size of these quantum dots, you can precisely control their optical properties, like the color of light they emit.
Change the size, change the color. Cool. Third type.
Third are dendrimers. These are nano-sized polymers built from branching units. Think of them like tiny, perfectly branched trees.
Okay.
A key characteristic of dendrimers is that they have multiple chain ends, which can be precisely tailored to perform specific chemical functions, making them promising for catalysis. Additionally, because these three-dimensional dendrimers have internal cavities, they can encapsulate other molecules.
Like carrying drug.
Exactly, making them potentially useful for targeted drug delivery.
And the fourth type.
And finally, composites. These involve mixing nanoparticles with other nanoparticles or embedding them within larger bulk-type materials.
Like adding nanoclay to plastic car parts.
That's a perfect example. Nano-sized clays are already being added to products ranging from auto parts to packaging materials. The purpose is to enhance their mechanical, thermal, barrier, and fire-resistant properties. You improve the bulk material by adding a little bit of nanomagic.
So these unique properties, electrical, catalytic, magnetic, mechanical, thermal, imaging, make them really desirable across many sectors.
Highly desirable, yes. For industrial, medical, service, and environmental sectors. These materials can also be incorporated into more complex nanostructures and systems. As new applications for these unique properties are discovered, the number of products containing nanomaterials and their potential uses continues to expand rapidly.
Can we break down those properties further? Physical properties?
Sure. On the physical side, we look at aspects like their precise dimension and shape, their specific surface area, the aspect ratio, how long versus how wide they are, how they agglomerate or aggregate, their pore size, their external morphology or topography, their internal organization like crystalline structure, and their solubility. All these matter.
And chemical properties.
And then there are the crucial chemical properties, their structural formula and molecular organization, their composition, including purity and any impurities. There's surface chemistry, things like charge, reactivity, or photocatalytic properties, and their hydrophilicity or lipophilicity.
How much they like water or oil.
Exactly. How they interact with water or fats. All these characteristics are vital for how nanomaterials function and interact with their environment.
So after more than 2 decades of dedicated nanoscience research and over a decade under the National Nanotechnology Initiative, nanotechnology applications are truly delivering on their promise to benefit humanity.
Yes, in both expected and sometimes surprising ways. Nanotechnology is visibly improving and in many cases revolutionizing countless products and industry sectors. We're talking information technology, energy, environmental science, medicine, homeland security, food safety, and transportation, among many others. The list of applications and benefits is growing at an incredible pace.
Let's consider some real-world examples. Adding nanoscale components to polymer composites in items like baseball bats, tennis rackets, bike helmets, car bumpers, and electronic device housings, that makes them better.
It can make them lighter, firmer, stronger, and more flexible. This directly translates to more durable and higher performing products.
What about fabrics?
Think about nanoscale treatments applied to fabrics. These can help clothes resist wrinkles, stains, and bacterial growth, or even provide a degree of ballistic protection in personal body armor. Imagine clothing that practically cleans itself or offers enhanced safety.
And then there are nanoscale thin films used on eyeglasses, computer and camera displays, windows, and other surfaces. What do they do?
These films can make surfaces water-repellent, anti-reflective, self-cleaning, resistant to UV or infrared light, anti-fog, antimicrobial, scratch-resistant, or even electrically conductive. Imagine windows that clean themselves or phone screens that never fog up.
Wow. And in personal care products, sunscreens, lotions.
In personal care products, nanoscale ingredients provide greater transparency or improved feel, enhanced cleansing properties, and antioxidant, antimicrobial, or other health benefits. You'll find these in sunscreens, cleansers, skin treatments, creams, lotions, shampoos, and specialized makeup. It's about enhancing everyday products at a fundamental level.
And in the food industry, nano-engineered components are being used in food packaging.
Right. Nanocomposites in containers can reduce carbon dioxide leakage from carbonated beverages or decrease oxygen and moisture penetration and even inhibit bacterial growth. The result, food stays fresher, safer, and lasts longer.
So if we categorize these applications by sector, you'll see just how widespread the impact is in electrical and information technology.
Nanotechnology is being applied in computing, communications, and other electronic devices to create faster, smaller, and more portable systems that can manage and store increasingly large amounts of information. This includes nanoscale transistors.
Making chips smaller and faster?
Exactly. Designed to be faster, more powerful, and more energy efficient, meaning that eventually your entire computer's memory could be stored on a single tiny chip.
Okay, what about sustainable energy? That's a huge area.
It is. Addressing the world's growing energy demand while protecting our environment is a critical challenge. Many scientists are exploring ways to develop clean, affordable, and renewable energy sources, as well as methods to reduce energy consumption and environmental toxicity.
Like better solar panels.
For example, yes, solar panels incorporating nanotechnology are far more efficient at converting sunlight into energy, offering more cost-effective solutions. Currently, nanostructured solar cells are cheaper to manufacture and easier to install
Oh.
because they can use print-like production processes and be made in flexible rolls instead of rigid panels. Newer research even suggests that future solar converters might be paintable.
Paintable solar cells.
Imagine making solar energy incredibly accessible and integrated into everyday surfaces.
In environmental remediation, beyond lighter vehicles that use less fuel and new energy sources, nanotechnology offers numerous applications for environmental cleanup.
Right. This includes tools that can purify dirty water on both large and convenient scales, and technologies that can detect and clean up environmental contaminants.
How does it help with water purification?
Nanotechnology can help provide affordable, clean drinking water through rapid, low-cost detection of impurities and efficient filtration and purification. For instance, researchers have discovered unexpected magnetic interactions between ultra-small iron oxide particles, which can help remove arsenic or carbon tetrachloride from water.
Interesting.
They are also developing nanostructured filters that can remove viruses from water and investigating deionization methods using nano-sized fiber electrodes to reduce the cost and energy required to remove salts from water. Lots of different approaches.
When it comes to nanobiosystem health, nanotechnology has the real potential to improve a wide range of diagnostic and biotechnology tools and procedures.
Making them more adaptable, convenient, cheaper, safer, and easier to use. A major advance in this area is the use of quantum dots.
Those color-changing crystals again.
Exactly. These are semiconducting nanocrystals that can significantly enhance biological imaging for medical diagnostics. When illuminated by ultraviolet light, quantum dots emit a wide range of vibrant colors. This property allows them to be used to precisely locate and identify specific types of cells and biological activities.
Better than current dyes.
Much better. These crystals can offer visualization that's up to 1,000 times better than conventional dyes used in many biological tests, like MRIs, providing significantly more information, a clearer picture, literally.
And finally, in transportation.
In addition to helping build and maintain lighter, smarter, more efficient, and greener trucks, planes, and boats, nanotechnology offers various ways to improve communication systems within transportation. Nanoengineering of steel, concrete, asphalt, and other cement-based materials holds great promise for improving the performance, resilience, and durability of road and moving infrastructure, while also reducing costs.
And maybe even add new functions.
Possibly. Future systems might even integrate innovative capabilities into traditional transportation infrastructure, such as the ability to generate or transmit power. Imagine roads that power streetlights.
Okay, let's expand on some of the more surprising and broad-ranging uses. You mentioned sensors earlier.
Yes. Many types of sensing elements, such as carbon nanotubes, zinc oxide nanowires, or palladium nanoparticles, can be used in nanotechnology-based sensors. Because of their incredibly tiny size, just a few gas molecules are enough to alter the electrical properties of these sensing elements.
Making them incredibly sensitive.
Extremely sensitive. Nanotechnology is already being applied across telecommunications, automotive, energy systems, IT sectors, medical devices, life science genomics, and industrial process control and instrumentation.
Let's talk about carbon, such a fundamental element.
It really is. Carbon, the sixth heaviest element, with an atomic mass of 12, 6 protons, 6 neutrons, plays an extraordinary role. Its isotope C14, which transforms into nitrogen over 5,730 years, is famously used for carbon dating in biology.
And its bonding makes it special.
Exactly. Carbon's unique properties, due to its 4 bonding electrons, explain its immense importance in the natural world, forming the very building blocks of all living organisms. It's incredible to think that most natural carbon molecules are currently impossible to synthesize chemically. For now, we simply marvel at and utilize these natural products that have evolved over eons.
And carbon exists in various forms, from diamond.
The symbol of perfection, those incredibly hard gemstones formed under extreme temperature and pressure deep within the earth.
To graphite.
Right, found abundantly in certain sediments. Graphite is made up of layers of graphene sheets, stacked like pages in a book with weak bonds between them. What's particularly significant for nanotechnology are 2 specific types of carbon nano-objects, nanodiamonds and carbon nanotubes.
Tell me about nanodiamonds.
They're produced, for example, by plasma spraying techniques. They consist of thousands of atoms, and their enhanced hardness is used to create specific coatings. When treated to be luminescent, they can serve as single photon sources for quantum cryptography. And if coated with active molecules, these nanocrystals become excellent biological probes for analysis and confocal microscopy. Very versatile.
And carbon nanotubes,
Yeah.
probably the most famous ones.
They are perhaps the most famous nanostructures. Their discovery dates back to experiments involving the electric arc vaporization or laser radiation of carbon atoms, which initially produced strange structures like fullerene C60.
The buckyball.
The buckyball, yeah. A molecule of 60 carbon atoms with a soccer ball-like structure. Scientists soon learned to create closed, rolled structures, forming single or multi-walled tubes just a few nanometers in diameter. The remarkable physical and chemical properties of these atomic grids have opened up countless avenues for scientific study. You can actually visualize their single or multiple inner walls using a transmission electron microscope.
Their mechanical properties are truly astounding, aren't they? What, 10 times harder than iron?
That's right. This characteristic can significantly enhance the resistance of textiles and composite plastic materials when they are incorporated as reinforcing agents, much like rebar in concrete. This is typically achieved by depositing ionized atoms in high-frequency heating ovens.
And the fullerene discovery got a Nobel Prize.
It did. It's worth remembering that the discovery of fullerenes by chemists H. Kroto, R. Curl, and R. Smalley earned them the Nobel Prize for Chemistry in 1996, a major milestone.
Electrically, they're also interesting for miniaturization.
Yes, from an electrical perspective, these structures are particularly attractive for creating electronic components at levels of miniaturization never before achieved by silicon technology. In fact, the smallest transistor in the world was made at the nanometer scale using these principles.
But there are challenges.
Oh, yes. Significant challenges remain in creating complex circuits with nanotubes. They don't yet offer fully reliable solutions, and the reproducibility of their electrical characteristics isn't perfect. It's also important to acknowledge that current silicon technology still has considerable potential before this new technology is fully mature.
Where do they show more immediate promise? Biosensors.
That's a key area. Where nanotubes show particular promise is in biosensors. Chemists have developed techniques to attach specific molecules to biosensors. These molecules can then bond with other target molecules in a particular environment, allowing for highly sensitive analysis and the creation of incredibly high-quality detectors.
And even drug delivery.
These nanotech-enabled machines could even potentially be used for targeted drug delivery inside the human body. Still early days for that, but the potential is there.
What about solar cells and screens?
Even though we currently can't produce nanotubes with perfectly homogeneous electrical characteristics, we can create nanotube deposits on semiconducting substrate surfaces. This opens the door to creating low-cost solar cells and circuits that can be used for transparent electrodes and flat screens with electroluminescent diodes once properly calibrated. Lots of potential there.
It's hard to fully grasp the immense potential of nanotechnologies. Operating at the atomic and submolecular levels has truly paved the way for major breakthroughs in chemistry, biology, and medicine.
Absolutely. Yet the practical applications of nanotechnology are far broader and more diverse than many might initially imagine.
Like filmmaking, for example. That seems unexpected.
It does, but without the invention of the scanning tunneling microscope, or STM, in the 1980s, nanotechnology might have remained largely in the realm of science fiction. The STM's incredible precision allowed scientists to image and manipulate materials in ways previously impossible. IBM famously demonstrated the STM's potential by creating A Boy and His Atom, the world's smallest animated film.
Moving individual atoms.
Exactly. Moving individual atoms on a copper surface to create frames. Mind-boggling stuff.
Okay, what about oil recovery?
The costs for oil exploration have skyrocketed, yet oil recovery rates remain surprisingly low. Often, less than half of the oil in a well is extracted before it's shut down, trapped in formations too expensive to access.
So nano helps get more oil out.
It seems so. Nanotechnology offers a solution. Scientists in China have found a way to enhance a drilling technique by injecting water laced with nanoparticles into the well to dislodge and drive out more oil.
Interesting. And high-resolution displays, making pixels smaller.
Essentially, yes. Traditional computer screens display images using tiny dots called pixels. More pixels usually meant larger, bulkier screens. However, scientists at Oxford University have developed a method to create pixels just a few hundred nanometers across, enabling far higher resolutions in much smaller packages.
And color-changing paint, using gold nanoparticles.
Yeah, that's a fascinating one. While researching strings of gold nanoparticles, scientists at the University of California made an amazing discovery. The color of gold changes when a thread of its particles is stretched or compressed. It can produce a stunning bright cobalt that morphs into purple and then scarlet.
Wow. What's the application?
This finding has inspired scientists to create antennas from gold nanoparticles that change colors when pressure is applied to them, potentially signaling mechanical stress or strain in materials.
Okay, phone charging. Everyone wants faster charging.
Definitely. Every smartphone user knows the two main downsides: battery life and recharge time. While battery life is still an ongoing challenge, scientists in Ramat Gan, Israel, have tackled the recharge time problem by developing a battery that requires only a 30-second refresh.
30 seconds. That would be amazing.
Wouldn't it just?
What about advanced drug delivery, making treatments cheaper and better?
That's a huge goal. Treatments for diseases like cancer can be prohibitively expensive and often ineffective, with significant side effects. Medical firms are actively researching cheaper and more efficient ways to deliver medicines. For example, Immusoft is exploring how nanotechnology can transform drug delivery within the human body, making treatments more targeted and less impactful on healthy tissues.
Molecular communication. That sounds like transmitting data molecule by molecule.
It addresses critical issues where electromagnetic interference could render communication satellites and other technology ineffective. Think of a doomsday scenario, where an electromagnetic pulse takes out all our electronics. Researchers from Warwick in the UK and York in Canada have been exploring unexpected solutions to these challenges using molecular-level communication. Still very experimental, though.
And computer storage. Moore's law is hitting limits. Right?
Many believe so. Over the past few decades, computers have seen exponential growth in both processing power and storage capacity, famously described by Moore's law. However, many scientists, including physicists, believe that Moore's law is reaching its limits with existing semiconductor technologies. Nanotechnology offers a new path forward, pushing past those limitations, potentially.
And finally, there's nano-art.
Yes. The incredible expansion of nanotechnology has captivated the scientific community. But breakthroughs aren't just limited to medicine, environmental science, and industrial applications. Nanoart is an emerging field that allows us to view the microscopic world through a completely new lens, transforming scientific images into aesthetic and mesmerizing experiences. Science meets art at the smallest scale.
Let's revisit nanomedicine and expand on its exciting possibilities. From truly visionary concepts to what's currently being tested and used.
Right. Nanotechnology in medicine encompasses applications of nanoparticles already in development, as well as longer-range studies involving the use of artificial nanorobots for cellular maintenance and repair. Regardless of how you describe it, the use of nanotechnology in medicine has the potential to revolutionize how we detect and treat damage to the human body and disease in the future.
And things that seemed like science fiction are getting closer.
Many practices that were only imagined a few decades ago are making significant progress towards becoming realities.
Now, food nanotechnology. This is where it gets maybe a bit controversial for some people.
It can be. This field has begun to explore potential applications in functional foods by engineering biological molecules for diverse functions, often very different from their natural roles. This is opening up entirely new areas of research and development.
It sometimes feels like there are no limits to what food technologists can do to our food, and nanotechnology offers them a whole new set of tools to push new boundaries. You mentioned nano-engineered violet.
That was perhaps a provocative example to illustrate the point. But there are also significant positives, particularly concerning the potentially beneficial effects that nanotechnology-enabled innovations could have on our foods and, consequently, on our health. Think better nutrient delivery or pathogen detection.
Okay, what about agriculture nanotechnology?
Applications are currently being researched and tested, and in some cases already applied across the entire spectrum of food science, from cultivation to food processing, packaging, and nutrient enhancement. While there have been tentative contributions despite numerous potential rewards and rising trends, many agricultural applications haven't yet reached the commercial market.
Why not? What's holding it back?
Several factors explain this scarcity of commercial applications. Industry experts suggest that agricultural nanotechnology doesn't yet offer sufficient economic returns to justify the high initial production investments.
It's expensive to get started.
Right. Additionally, new nanotech regulations within the EU could create regulatory uncertainty for products already on the market and influence public perception. However, current studies suggest that public opinion isn't generally negative towards nanotechnology, and the introduction of nanotech products with clear benefits will likely drive consumer acceptance.
So it might just take time.
Possibly. The rapid advancements of nanotechnology in other key industries may eventually transfer to agricultural applications, helping to accelerate their adoption. The key takeaways here are that nanotechnology represents a new source of progress for the agricultural sector, but nano-related applications in farming are not yet widespread commercially, and both education and public engagement are fundamental to shaping how these products are received for decades to come.
Nanotechnology is also making significant strides in water purification.
Yes. Advances in nanoscale science and engineering suggest that many of the modern challenges related to water quality could be resolved or greatly improved using nanosorbents, nanocatalysts, bioactive nanoparticles, nanostructured catalytic membranes, and advanced nanoparticle filtration, among other products and processes.
Especially for desalination, removing salt.
Improvements in developing novel technologies to desalinate water are among the most exciting and promising. Furthermore, nanotechnology-derived products that can reduce the concentration of harmful compounds to undetectable levels can significantly help achieve stringent water quality standards and health advisories. We're talking about making water incredibly clean.
Moving to mechanical and civil engineering, how can nano help build things?
Nanotechnology can be used for inventing and enhancing structures in countless ways, as nanotechnology-engineered materials possess unique characteristics. This includes materials for lighter constructions, stronger structural composites for bridges, low-maintenance coatings, improved sound insulation, superior properties for cementitious materials.
Like better concrete.
Essentially, yes. Also, reducing the rate of heat transfer and fire retardants in insulation, increasing the sound absorption of acoustic dampeners, and boosting the reflectivity of glass. Lots of potential improvements.
In the construction industry, energy conservation is a big deal. Does nano help there?
It does. The use of nanomaterials needs to be considered not just for their attractive properties and function, but also, importantly, in the context of energy conservation. This is crucial because a large portion of all energy consumed is absorbed by commercial buildings and residential dwellings through applications like heat transfer, illumination, and temperature control.
So better insulation, maybe.
Better insulation, smarter windows, coatings that reflect heat. Financial assessments suggest nanotechnology has a considerable impact on the manufacturing sector. Some applications have been developed specifically to enhance the stability and performance of building materials, improve energy efficiency, and increase the safety of buildings, while also facilitating easier maintenance and providing greater comfort for occupants.
And self-cleaning surfaces.
While self-cleaning surfaces have been achievable through micron-sized coatings, for example, Teflon or polysilicon-based coatings, this feature has now become a major selling point for nanotechnology, especially in consumer markets like construction and textiles. Nano makes it even better.
Nanocatalyst applications are also expanding rapidly. Catalysts speed up chemical reactions, right?
Exactly. In this era of nanotechnology, where the size of everything is shrinking, their superior properties mean that nanoscale materials are widely used in various chemical processes and offer significant benefits. We've seen a vast amount of literature on the application of nanocatalysts in recent years, particularly in the photocatalytic degradation of pollutants like phenol.
Why are nanoparticles better catalysts?
Because of that huge surface area, again, nanoparticle catalysts are incredibly active because a large majority of the particle surface can be exposed to the catalytic reaction. There's just more active space for the reaction to happen.
Where are they used?
Many of these nanocatalysts have found applications in ammonia synthesis, environmental protection via photocatalysis, waste removal, and even in fiber and mechanical production. The specific effect of nanocatalysts for the photocatalytic breakdown of phenol is particularly significant, as phenol and related compounds are widely distributed pollutants.
So bringing it back to the everyday, nanotechnology in everyday life is already here.
It truly is. It's become an undeniable part of modern living, both at work and at home. Think about the clothes you wear, your eyeglasses, computer hard drives, and even cleaning products. Nanotechnology, often inspired by the natural world, plays a significant role in the production of many familiar items. Even things we've used for a long time can now contain nano-engineered components, like the lasers inside various devices, according to experts in the field.
Looking to the future uses of nanotechnology, it's been called the science of the 21st century.
It has. Its potential impact is often compared to the early days of the semiconductor industry, or the boom in biotechnology in the last century. Interestingly, the likely application of nanotechnology is a combination of both semiconductor and biotechnology advancements.
It's not really a standalone technology, though, is it? It builds on others.
That's a key point. It's important to understand that nanotechnology isn't a sovereign technology like, say, molecular ecology. Nanomaterials are created through fundamental sciences like chemistry, physics, and in some cases, even environmental science, utilizing microorganisms and plant life. The applications of nanomaterials involve both basic and applied sciences and engineering.
So where will we see it more?
For instance, nanomaterials are already being used and will be increasingly used within semiconductor manufacturing to improve integrated circuit development. They are also being explored and applied for drug delivery, molecular environmental science, food monitoring, barcoding, threat agent monitoring, anti-counterfeit currency measures, disinfection, environmental monitoring, advanced paints and coatings, catalysts for various reactions, and agricultural improvements.
But there's still a long way to go.
Oh, yes. There is still an immense amount of work to be done before we fully realize the superior tools that can emerge from nanotechnology, which is still in its infancy. However, predictions suggest that in just 5 more years, a significant number of its commercial products will be widely available in the market for various business and consumer uses. Things are moving fast.
Let's transition now to engineering at the smallest scale, focusing on NEMS and MEMS. What exactly are nano-electromechanical systems, or NEMS?
Okay, NMs involve crucial structural elements that are at or below 100 nanometers. That's the key differentiator. This is what fundamentally distinguishes them from micro-electromechanical systems, or MEMS.
Which are micro, not nano.
Right, where the key structural elements are on the micrometer scale. Compared to MEMS, NEMS combine a much smaller mass with a significantly higher surface area to volume ratio, making them particularly exciting for high-frequency resonators and ultra-sensitive sensors.
So NEMS are basically the next step down in size from MEMS.
You can think of them as the logical next tininess step from MEMS, yes. NEMS represent a class of devices that seamlessly integrate electrical and mechanical functionality at the nanoscale.
How do they work?
NMS inherently connect transistor-like nanoelectronics with mechanical mechanical actuators, pumps, or motors. In doing so, they can form incredibly sensitive physical, biological, and chemical sensors. Their name comes from typical device dimensions in the nanometer range, which results in low mass, high resonant frequencies, potentially significant quantum mechanical effects like zero-point energy, and a large surface-to-volume ratio that's beneficial for surface sensing mechanisms.
What are they used for?
Uses include accelerometers, maybe in your phone, or detectors for chemical compounds in the atmosphere. A key application for MEMS is in atomic force microscopes, where the increased sensitivity provided by NEMS leads to smaller, more efficient sensors capable of detecting stresses, vibrations, forces, and chemical signals at an infinitesimal level.
Okay, now what about MEMS themselves? Microelectromechanical systems.
MEMS refer to the technology of miniature devices, primarily those with moving parts. They converge with nanotechnology at the nanoscale to form NEMS, as we just discussed. MEMS are also known as microapparatus in Japan, or microcoordination technology in Europe.
And they're distinct from molecular nanotechnology.
Yes, it's important to note that MEMS are a distinct field from the more visionary concepts of molecular nanotechnology or molecular electronics. MEMS components are typically between 1 to 100 micrometers in size.
Still tiny, but much bigger than nano.
Exactly. 0.001 millimeter to zero point 0.1 millimeter. And complete MEMS devices usually range from 20 micrometers to a millimeter. They commonly consist of a central processing unit for data and various components that interact with the environment, such as microantennas or sensors.
And physics works differently at that scale, too.
It does. At this size scale, the conventional physics we're used to doesn't always apply perfectly. Because of the large surface area to volume ratio of MEMS, surface effects like electrostatics and surface tension become more dominant than bulk properties like inertia or thermal mass. Surface forces rule.
And Feynman predicted this, too.
He did. The potential for incredibly tiny devices was recognized even before the technology existed to make them. As highlighted in Richard Feynman's famous 1959 lecture, there's plenty of room at the bottom.
So how did they become practical?
MEMS only became practical once they could be fabricated using adapted semiconductor device manufacturing technologies, typically used for electronics. These include processes like molding, plating, wet etching, dry etching, and electrical discharge machining, all capable of producing miniature devices. An early example of a MEMS device is the resonator and electromechanical mass resonator, basically tiny vibrating structures.
The thin film deposition process sounds critical for making these microsystems.
It is. It allows for the precise placement of thin film layers ranging from just a few nanometers up to 100 micrometers in thickness. For example, a thin film of silicon nitride can be used as the diaphragm for a MEMS pressure sensor. The controlled deposition of these thin films is one of the essential steps in MEMS manufacturing.
What are the main methods? PVD.
One method is physical vapor deposition, PVD. This process involves a substance being transferred from a source material or target and deposited onto a desired surface, the substrate. PVD techniques include sputtering, where energetic ions dislodge atoms from a target, allowing them to travel through a vacuum and deposit on the substrate.
Okay. Another is evaporation, where a substance is evaporated from a target using heat or an electron beam in a vacuum system. The result is the direct physical deposition of materials onto the substrate, creating uniform thin films.
Then there's chemical vapor deposition, CVD. How is that different?
Here, a flow of source gases reacts on the substrate surface to produce the desired material. It's a chemical reaction happening right on the surface. This can be further categorized based on the process conditions, for example, low-pressure CVD, LPCVD, and plasma-enhanced CVD, PCVD.
And you can grow oxides, too.
Right. Oxide films can also be grown through thermal oxidation, where the wafer is exposed to oxygen and/or steam to grow a thin surface layer of silicon dioxide. In essence, these processes deposit thin films based on chemical reactions happening at the surface.
CVD comes in different flavors, right? Based on pressure. It does. CVD is adaptable and used in many formats, generally varying in how the chemical reactions are initiated. Classified by operating pressure, we have atmospheric pressure CVD, APCVD, low pressure CVD, LPCVD, which reduces unwanted gas phase reactions and improves film uniformity, and ultra-high vacuum CVD, UHV-CVD, at very low pressures. Most modern CVD processes are either LPCVD or UHV CVD.
And classified by the physical characteristics of the vapor.
We find aerosol-assisted CVD, AACVD, where precursors are transported to the substrate via an aerosol generated ultrasonically. This method is suitable for non-volatile precursors. And there's direct liquid injection CVD, DLI-CVD, where liquid precursors or solids dissolved in a solvent are injected into a vaporization chamber and then transported to the substrate. This process is ideal for liquid or solid precursors and can achieve high deposition rates. Different tools for different jobs.
Okay, the etching process. This is like sculpting at the micro and nanoscale.
That's a good way to put it. It's fundamental to nanotechnology production. Industrialization at the infinitesimal scale could trigger its own mini-industrial revolution. However, moving from laboratory systems to mass fabrication of tiny features requires overcoming significant challenges.
Making lots of tiny things reliably is hard.
Exactly. While volume production is promising for objects as small as the tens of millions of transistors on a processor chip, the etching processes used to make them, like photolithography, have limitations. Photolithography has a practical limit of about half the wavelength of the light used, making it difficult to produce features smaller than 100 nanometers. To date, mass production etching techniques, which use a solvent to remove material and create patterns, haven't been able to make features any smaller.
But Cornell researchers found a way.
Yes, a group of researchers at Cornell have developed an etching process that can create regular patterns with features as closely spaced as 38 nanometers. To truly grasp that scale, a nanometer is 1/1,000,000th of a millimeter, or roughly the length of about 10 carbon atoms linked together.
What does this enable?
This process creates simple, elegant surfaces, but these could serve as the building blocks for more complex structures. This work has the potential to contribute to mass production techniques for creating small-scale lattices, forms, individual parts, and ultimately tiny circuits and machines.
How does the technique work?
The method involves bonding skewed, single crystal layers of silicon. The misalignment between these layers causes weak atomic bonds to form in areas where the atoms are not perfectly matched. These imperfections or linear defects appear within the bonded silicon. The researchers then apply an etchant, an etching solution to the surface, which preferentially dissolves these dislocations, these weak spots, leaving tiny grooves. The key is applying the etching solution for precisely the right amount of time. Too short or too long, and it doesn't work.
What do they demonstrate?
To demonstrate the process, the researchers fabricated a silicon surface with bumps just 5 nanometers high, 26 nanometers across, and spaced an average of 38 nanometers apart. This technique can theoretically be used to form patterns with features separated by as little as 2 nanometers.
Wow, but hard to see.
Extremely. To view features and spacing that small, the researchers needed to enhance the magnification of their atomic force microscopy by modifying the microscope tips with carbon nanotubes. For context, the gap between binding sites on individual antibodies is about 10 nanometers, and the width of a single attachment point is about 2 nanometers. So we're talking truly molecular dimensions.
Thermal oxidation is another vital deposition technology. How does this one work?
It's essentially the controlled oxidation of a substrate surface in an oxygen-rich environment. You basically grow an oxide layer. The temperature is typically raised to 800 degrees, 1100 degrees C to speed up the process.
And it uses up the substrate.
Yes. This is unique because it's the only deposition technology that actually consumes some of the substrate as it progresses. The growth of the film happens downwards as oxygen diffuses into the substrate. As the oxidized layer thickens, the diffusion of oxygen becomes more difficult, leading to a parabolic relationship between film thickness and oxidation time for films thicker than about 100 millimeters. It slows down as it gets thicker.
So it's mainly for making oxides.
Right. This process is logically limited to materials that can be oxidized and can only create films that are oxides of that material. It's conventionally used to form silicon dioxide on a silicon substrate, a cornerstone of chip manufacturing.
How is it used in nano-imprint lithography, NIL?
In nano-imprint lithography, or NIL, a straightforward thermal oxidation process is used to reduce the feature size of NIL masters, the molds used to create patterns.
How does that work?
Through oxidation, the dimensions of negative features, like gaps, become narrower, while the dimensions of positive features, like lines, become wider. We've seen that positive feature sizes can also be further reduced after etching by selectively patterning the oxide. For instance, 74 millimeter gaps can be reduced to 10 millimeters, and 226 millimeter lines can be narrowed to 55 millimeter.
So it helps make finer patterns.
Exactly. This reduction in feature size directly translates into greater patterning capabilities and enhanced resolution in NIL for creating precise replicas from thermally oxidized NIL masters.
And NIL itself is important.
Yes. Nanoimprint lithography is a conceptually simple method for patterning high-resolution features on a substrate. For pattern transfer using NIL, a rigid master with nanoscale relief features is pressed into a soft resist, which then takes on the negative impression of the master's pattern. To optimize the process, parameters like imprint pressure and temperature can be varied, and the pattern can be exposed to UV or other wavelengths during the process. NIL allows for high-throughput patterning, and features as small as 5 millimeters have been successfully demonstrated.
Is the industry adopting it?
Because of these attributes, the International Technology Roadmap for Semiconductors, which guides the semiconductor industry, has embraced NIL as a promising method for reaching sub-22 nanometer technology nodes, which are beyond the capabilities of conventional photolithography. If requirements for speed, alignment precision, defect control, and resolution can be met, NIL could become the ideal technology for fabricating the next generation of integrated circuits.
Other applications too.
Yes, applications with less stringent process requirements also exist, such as in solar cells, lighting, displays, and molecular electronics. As a result, NIL is expected to become an increasingly important tool in both academic research and full-scale industrialization.
Finally, let's talk about casting for manufacturing nanowires. Making these incredibly thin wires consistently is a challenge, right?
It is. These incredibly tiny wires, a mere 10,000th the width of a human hair, could theoretically be used to create materials with novel electrical, optical, and mechanical properties. But before engineers can turn them into practical applications, these nanowires, which are just a few nanometers wide, need to be consistently produced in huge quantities, whether as wires, strips, or tubes.
How are they usually made?
Currently, nanofibers are made in various ways, none of which are completely satisfactory. One uses lithography and evaporation, similar to steps in silicon chip manufacturing. Another is screen printing, being developed for various materials.
And electrospinning.
A third method, electrospinning, dates back to the 1930s. In this technique, an electrically charged syringe expels a polymer solvent mixture towards an oppositely charged electrode. The voltage difference creates a jet of the solution, and as it travels, the solvent evaporates, leaving behind a solid fiber.
What's the downside?
While this technique works, the fibers tend to accumulate in a tangled mess, often described as project of spaghetti, not very ordered.
But Minfeng Yu at Illinois found a better way.
Yes. The fibers produced by Yu's method are smooth, continuous, and surprisingly long. Each nanofiber is only nanometers in diameter, but the longest one Yu created stretched for half a meter, and he only stopped because he grew tired of winding it onto a small pin. In theory, his method should be able to produce nanofibers of any length.
How does it work?
His technique, like electrospinning, relies on dissolving the material that will become the fiber in a solvent. The tip of a micropipette, just 100 nanometers in diameter, is used to draw out the start of the filament and pull it across a surface where it can dry. As the solvent evaporates, the material solidifies.
And you just keep pulling.
From then on, it's simply a matter of reeling in the fiber. As long as the thread doesn't break, it can be extended indefinitely. By precisely moving the pipette both horizontally and vertically, it's possible to create three-dimensional structures with much more order than a tangled pile of spaghetti, enabling section fabrication, like 3D printing with nanofibers.
Is it fast enough for commercial use?
According to Yu, his technique can produce fibers at a speed of 3 millimeters per second, which bodes well for scaling it into a commercial process. It should provide an inexpensive way to manufacture nanofibers from a variety of materials, provided they are soluble in a fast-evaporating solvent. It also allows for the creation of new types of nanofibers for experimental research.
What are the future prospects? Labs on a chip?
One exciting prospect Yu envisions is embedding these fibers into materials like plastic blocks and then dissolving them to create tiny channels for fluid flow. This would make it easier to construct labs on a chip, which are used for various types of chemical analysis. Another idea is to create rooted fibers from pairs of materials which, when combined within a core, could react to produce combined useful electrical or mechanical properties. Lots of interesting possibilities.
Okay, let's explore nanoelectronics. This is using nanotechnology in electronic components and devices.
Exactly. Nanoelectronics refers to the application of nanotechnology in electronic components and devices. This term covers a diverse range of approaches and materials, but the common characteristic is that these systems are so miniature that interatomic interactions and quantum mechanical properties become critically important considerations.
So it's electronics where quantum effects matter.
Pretty much. Nanoelectronics involves using nanotechnology in electronic devices. The term encompasses a diverse set of techniques and materials, all characterized by their incredibly small scale, where interatomic forces and quantum mechanical properties must be extensively considered. Candidate technologies include hybrid molecular semiconductor electronics, rudimentary nanotubes and nanowires, or more complex molecular electronics.
And current chip technology is already there.
It's quite remarkable that current silicon CMOS technology, such as the 22-nanometer node, is already operating within this nanometer scale. Nanoelectronics is often considered a disruptive technology because many of the emerging contenders are significantly different from traditional transistors.
But it's still early days.
Even with all the incredible modern innovations, nanoelectronics is still in its early stages. We currently lack a comprehensive theory that can consistently predict the results of electrically stimulating single molecules. To fully realize the immense potential of nanoelectronics, scientists need a unified theory of conductance through molecular structures. We're still figuring out the fundamentals.
So what are the core benefits of nanotechnology in electronics? Faster, smaller, more portable.
That's the headline, yes. It's essential to understand that nanotechnologies are being used in countless designs, forms, and electronic applications. They offer faster, smaller, and more portable systems that can process and store ever larger amounts of information.
Where do we see it now? Memory chips? Coatings?
Yes. Nanotechnology in electronics is already present in many products. Think about the flash memory chips in your devices like an iPod Nano, or even the antimicrobial and self-cleaning coatings on computer mice and phone casings.
The fundamental goal is using those unique nano properties for information processing.
Exactly. The fundamental goal of nanoelectronics is to process, transmit, and store information by leveraging properties of matter that are uniquely different from those observed at macroscopic scales.
You mentioned MRAM, magnetic memory.
Yes, you'll find nanotechnology used in magnetic random access memory, or MRAM. This technology, enabled by nanometer-scale magnetic tunnel junctions, can rapidly and efficiently store even encrypted data during system shutdowns or crashes, allowing for instant resume play features. Faster and potentially uses less power than current RAM.
So overall, it means better performance, storage, maybe even quantum computing down the line.
Ultimately, yes. Nanotechnology in electronics provides advanced performance capabilities with conductive nanomaterials, improved data storage, the foundation for quantum computing, printable and flexible electronics, and efficient nanoparticles for data storage.
It could revolutionize things like transistors, diodes, displays.
Absolutely. Nanotechnology has the potential to truly revolutionize many electronic products, processes, and applications. This includes developing nanotransistors, nanodiodes, OLEDs, plasma displays, and even quantum computers eventually.
Plus better efficiency.
Furthermore, nanotechnology in electronics significantly increases the potential of electronic devices while simultaneously reducing their power consumption and energy footprint. This means more powerful devices that are also more energy efficient, a double win.
And making screens thinner and lighter.
Right. Nanotechnology is also advancing display panels on electronic devices. This allows for reduced power consumption and thinner, lighter screens, making our gadgets even more portable and sleek.
And packing more memory and transistors onto chips.
Exactly. Nanotechnology increases the density of memory chips and reduces the number of transistors needed in integrated circuits. In summary, in electronics, nanotechnology is providing faster, smaller, and more convenient systems across computing, communications, and various electronic applications.
Let's explore some basic applications, starting with the nanotransistor, the fundamental switch, but nano-sized.
That's it. A nanotransistor is a transistor, the fundamental component that acts as an electronic switch or amplifier scaled down to the nanometer level, about a billionth of a meter. The term nano comes from the Greek word for dwarf.
Are they in use yet?
While there isn't a nanotransistor of this precise scale in widespread practical use yet, significant advances towards achieving such an extraordinary component of nanotechnology are very promising. In November 2001, Bell Lab scientists announced their laboratory's ability to create individually addressable nanotransistors at the single-molecule level.
Single-molecule transistors. How many could fit on a pinhead?
Imagine, approximately 10 million such nanotransistors could fit on the head of a pin.
Incredible. Yeah. What was the breakthrough? Getting wires connected.
That was a key part. A key breakthrough in this Bell Labs research was overcoming the complex challenge of connecting electrodes to each molecule. They devised a self-assembly process that essentially allows the electrode contacts to form themselves, a procedure that doesn't require the ultra-clean room conditions of conventional fabrication.
Self-assembly solves the wiring problem.
It helps significantly. This new approach to a one-molecule transistor was detailed in a prominent science journal. An earlier approach to a nanotransistor, explained in late 1999, was described as a ballistic nanotransistor because its design allowed current to flow without the typical 65% energy loss seen in current transistors. More efficient flow.
Next, nanodiodes. This seems related to a European project.
Yes. Engaging with stakeholders and fostering public dialogue are critical for the responsible growth of nanotechnologies in Europe. The European FP7 project Nanodiode, launched in July 2013 for 3 years, established an innovative, coordinated program for outreach and discussion across Europe to support the successful governance of nanotechnologies. The initiative combines vital engagement activities along the innovation value chain.
From research to society.
Exactly. Covering research policy, research and development, and the societal use of nanotechnological innovations. Importantly, Nanodiode integrates upstream public engagement through dialogues that incorporate common requirements, ideas, and opportunities into policy discussions.
So getting public input early.
Right. It also involves midstream engagement by organizing innovation workshops at the level of R&D practices, which are at the core of research and innovation initiatives. And it uses a downstream approach for communication, outreach, training, and education. The partnership brought to bear a strong network of partners from diverse backgrounds across Europe.
Scientists, industry, public.
Yes, scientific, public research, industry, policy, civil society, education, and media organizations. Many participants leverage knowledge gained from earlier European nano-related projects. It was about building a coordinated approach.
Third, OLED, or organic light-emitting diode. These are in our phones and TVs now, right?
Many of them, yes. This is a type of light-emitting diode where the light-emitting layer is a natural organic compound that glows when an electric current passes through it. This thin layer of organic semiconductor is situated between two electrodes, at least one of which is typically transparent.
Where are they used?
OLEDs are used to create digital displays in devices like TV screens, computer monitors, and portable electronics, such as mobile phones, gaming consoles, and PDAs. A major area of research is the advancement of white OLED devices for use in solid-state lighting applications replacing light bulbs.
Are there different types?
There are two main families of OLEDs, those based on miniature molecules and those that use polymers. Adding mobile ions to an OLED creates a light-emitting electrochemical cell, or LEC, which operates somewhat differently. OLED displays can use either passive matrix, PMOLED, or active matrix, AMOLED control schemes.
AMOLED is common in high-end phones.
Right. AMOLEDs, with their thin film transistor backplane, allow for individual pixel control, enabling higher resolution and larger display sizes.
What are the benefits over LCD? Better blacks. Thinner.
Exactly. OLED display technology, because it doesn't require backlight, can achieve truly deep black levels and can be made thinner and lighter than a liquid crystal display, or LCD. In low light conditions, like a dark room, an OLED screen can achieve a significantly higher contrast ratio than an LCD, regardless of whether the LCD uses cold cathode fluorescent lamps or an LED backlight.
Innovations in nanotechnology promise to fundamentally change the forms and functionalities of electronic devices. It's more than just shrinking things.
Absolutely. Offering far more than just smaller versions of existing technologies, nanoelectronics researchers are applying the unique properties of individual components to transform how devices are designed, manufactured, and used.
What kind of transformation?
These advancements will enable the next generation of electronics. Ultra-efficient LEDs, personalized body sensors, flexible displays, and high-power, environmentally friendly energy equipment. While the field is still in its early stages, scientists at places like the University of Maryland, for example, are advancing both the practical applications and the fundamental theory of nanoelectronics.
Let's highlight some important specific uses of nanotechnology in electronics. First, nanotubes for advanced capacitors and electronic paper.
Right. Researchers are manufacturing the nanotubes and nanowires needed to create ultra-efficient capacitors components that store charge and light, flexible displays. By using precisely controlled synthesis methods for height and shape, they are designing ultra-fast electrochemical systems that can be readily transferred to commercial manufacturing.
Electronic paper, like a Kindle, but maybe flexible.
Potentially. Teams are currently collaborating with companies like Samsung to develop electronic paper display campaigns with high storage capability that can be handled and manipulated just like a piece of paper. The applications of these industrialized processes are only just beginning to be explored.
And maybe self-powering devices.
That's the ultimate strategy, to develop systems that integrate energy harvesting and storage to create self-powering devices. Imagine a cell phone that could recharge itself by harvesting solar energy through embedded nanostructures in its casing.
That would be incredible. Second, electron routing and flexible electronics using graphene.
Yes, work with graphene and nanotransfer techniques promises breakthroughs in displays, sensors, and even electronic fabrics. Graphene is a single atomic layer of carbon, quite distinct from 3D graphite. Scientists have successfully created absolutely pure graphene devices that exhibit unique bonding characteristics.
How does it help route electrons?
Electrons can be precisely guided along the graphene sheet to produce a range of electronic properties. It's like a tiny electronic highway. The nanotransfer printing technique, which researchers helped develop, allows for novel and cost-effective ways to integrate nanoelectronics into functional surfaces.
And these can be flexible.
Yes, these samples can be stretched, bent, or twisted, and are often transparent. Companies are leveraging this know-how to develop applications like low-profile, convenient contamination sensors and electronic fibers woven into materials.
What's the focus now?
Current focus is on refining semiconductor strategies at the nanoscale, tailoring graphene's properties for high-speed applications, and controlling the adhesion between different nanoelectronics components, making sure everything sticks together properly.
Third, chipless electronic devices. Electronics without a silicon chip.
That's the idea. Researchers are using pre-assembled carbon nanotubes and nanopatches to construct electronic structures that don't require traditional silicon chips. This means they have the potential to function on virtually any surface glass, plastic, or fabric.
What does pre-assembled mean here?
Pre-assembled refers to using simple, standard techniques to process source materials into functional nanoscale components before putting them onto the final surface. Teams are actively discovering new methods to build novel nanostructures and are exploring their electrical properties.
And nanotubes work well as transistors.
Research indicates that semiconducting nanotubes not only perform well, but can also be easily manipulated to change their functions. This finding suggests new capabilities for field effect transistors, which are the fundamental building blocks of most computer chips.
What's the hurdle?
In the future, the goal is to resolve the challenges of scaling up nanotube assembly for mass production. Making one is different from making billions reliably.
Fourth, beam deposition technologies. Using ion and electron beams.
Right. Nanoscale ion and electron beam fabrication offers critical expertise for semiconductor manufacturing. This work has significantly improved the security and speed of radio frequency identification, RFID tags.
Those little tags that replace barcodes.
Exactly, which are a potential substitute for barcode systems. This technology is also used in malfunction analysis, mask repair for chip making, and prototype chip design.
How else is it being applied?
In beam deposition research, collaborations have applied nanoscale local deposition methods to describe nanofibers, semiconductor nanowires, and carbon nanotubes. A recent development is a method for depositing metals with far higher purity than previously achievable processes. All these innovations contribute to improving chip performance.
What's next for this?
The future involves building prototype RFID tags and ultra-high vacuum chambers that would allow authentication of devices with even greater clarity and security, pushing the precision further.
Looking to the horizon, researchers are exploring the next generation of nanoelectronics, combining flexibility, simple production, and low power requirements, like plastic electronic circuits.
Yes, made from cadmium selenide nanocrystals deposited on synthetic sheets, offering new possibilities for flexible devices.
And silicon nanophotonics, using light instead of electricity inside chips.
That's the goal, amalgamating silicon nanophotonics workings into CMOS integrated circuits for higher momentum data communication between included routes than is probable with electrical indication. Light is faster than electrons for data transfer over distances.
Nanomagnets as buttons, lower power switches.
At UC Berkeley, researchers developed a near-to-ground power process using nanomagnets similar to transistors for greatly lower power expenditure than transistor-based pathways, a potential way to make electronics much more efficient.
Inkjet printed circuit boards. printing circuits.
Yeah, researchers at Georgia Tech, U Tokyo, and Microsoft Research developed process to produce example circuit boards using average inkjet printers with silver nanoparticle ink to form the conductive lines needed in circuit boards. Great for rapid prototyping.
Advanced lasers using nano-patterned silicon.
Caltech established a laser using nano-patterned silicon exterior for tighter incidence control, allowing much better information rate for fiber optics, boosting internet speeds and data transmission. More precise light signals.
Carbon nanotube transistors are still being worked on.
Definitely. Developing smallest transistor extent of a few nanometers, mounting techniques for integrated circuits. It's a major area.
And making functioning integrated circuits from them.
Stanford Academia established method to make functioning ICs with carbon nanotubes, including methods to eradicate clanging nanotubes, the metallic ones that cause shorts and deal with skewed ones, demonstrated 178 execution transistors in a simple circuit. Proof of concept.
Guide-free joins for space missions. Using copper nanoparticles.
Developing dependable joins for freedom missions and high-pressure environments using copper nanoparticles to make stronger, more reliable connections without traditional solder.
And flexible displays using nanowire electrodes.
Using electrodes completed from nanowires for flat sheet displays to be plastic and thinner than current rigid displays. Think roll-up screens.
Okay, let's shift our focus to nanomedicine. Healing at the smallest scale, expanding on what we've touched upon. It's the medical application of nanotechnology.
That's right. Its scope ranges from the medicinal appliance of nanomaterials and biological strategy to nanoelectronics biosensors, and even to the probable future application of molecular nanotechnology, like those theoretical organic equipment or cell repair machines.
But toxicity is still a concern.
Yes. Current challenges for nanomedicine involve accepting questions related to toxicity and ecological impact of nanoscale materials, those materials whose structure is at the nanometer scale. This is a crucial area of ongoing research to ensure safety as these technologies develop.
What's the near-term goal?
Yeah.
Better tools and devices.
Exactly. Nanomedicine aims to bring an expensive set of discovered tools and clinically practical devices in the close to potential. The National Nanotechnology Initiative expects new, profitable application in the pharmaceutical manufacturing.
Like better drug delivery.
Yes, sophisticated drug delivery organization, new therapies, and in vivo imaging seeing inside the body with greater clarity.
And the funding is there.
Yes, U.S. National Institutes of Health, for example, has been backing 4 nanomedicine midpoints for years. Market growth is significant. Sales reached $16 billion in 2015, $3.8 billion in R&D annually back then, and universal funding enlarged by 45% per year around that time. Creation sales over $1 trillion predicted in 2013. It's expected to have a noteworthy shock on the nation and the world.
Let's talk about bio-nanotechnology, using biology's tricks at the nanoscale.
That's a good way to put it. DNA and nanotechnology is a key model here. Focuses on operating inbuilt belongings of nucleic acids, like DNA, to create useful materials using DNA not just for information, but as a building material.
What else? Using proteins.
Other research is taking advantage of casing property of proteins to manufacture derivative membranes, and looking at self-assembling proteins for large-scale creation of programmable nanomaterials.
Like in biofilms.
Yes, for example, expansion of arm loads in bacterial biofilms as engineered nanomaterials genetically spontaneous to have dissimilar properties. Protein folding studies are also a third imperative avenue of investigation.
So predicting folding is hard.
Limited by inability to predict protein failure accurately, yes, but it has high importance for future bio-nanotechnology, given how natural systems use proteins for everything. Understanding that is key.
For nanobiotechnology sounds similar. Is it the same?
Often used interchangeably, but there's a subtle distinction, sometimes intended. It's the appliance of nanotechnology in biological fields, a multi-corrective pasture combining manufacturing physics, chemistry, biology. The terms nanobiotechnology, bio-nanotechnology, and nanoecology all pass on to the crossroads of nanotechnology and biology.
So what's the purpose?
It's used to designate the combination of biological investigate with various fields of nanotechnology. Concepts include nanodevices like biological equipment, nanoparticles with nanoscale occurrences within nanotechnology regulation. The goal is often to envision and produce associations for biological investigate.
And biologically inspired tech.
Right. Biologically inspired nanotechnology uses biological structure as stimulation for skill not yet shaped. Learning from nature's designs. And ethical issues are definitely part of the conversation here, too.
Can you clarify the terms of nanobiotechnology? Bio-nanotechnology versus nanobiotechnology.
Sure. While often used interchangeably, if a distinction is made, bio-nanotechnology usually focuses on applying biological ideas, understanding how biological equipment work, adapting biological designs to humanize existing nanotechnologies or generate new ones, building with biology's principles.
Okay. And nanobiotechnology.
Nanobiotechnology focuses more on ways nanotechnology is used to create strategy to study biological systems, essentially miniaturize biotechnology, using nanotools for biology.
So nanobio gives tools to study biology. Bio-nano rebuilds biological machines.
That's a good summary. Nanobiotechnology provides more tools for studying ecology. Bio-nanotechnology promises to restructure biological machinery.
Can you give examples?
Sure, DNA nanotechnology or cellular engineering would be bio-nanotechnology. Medical knowledge involving nanoparticles as liberation system or sensors would be nanobiotechnology.
Okay. What about the concepts of nanobiotechnology?
It receives most essentials from nanotechnology. Designs are straight based on other obtainable nanotechnologies. It often describes multidisciplinary behavior linked to biosensors, especially where photonics, chemistry, biology, biophysics, nanomedicine, and manufacturing congregate.
Like using waveguides.
Yes, for example, capacities in biology by waveguide performance, such as double division interferometer, using light to probe biological systems at small scales.
And the application in tools. Bio-nanotechnology is widespread.
The function of bio-nanotechnology is tremendously prevalent in nature. Nanobio knowledge is more ordinary in practice right now, as it purely presents more tackle for study of ecology. Bio-nanotechnology promises to restructure biological machinery in practical ways, which is perhaps the longer-term vision.
What kind of tools are used in research?
A whole range. Tentative tools like imaging and characterization, AFM optical tweezers, X-ray diffraction support tools, mixture by self-assembly, portrayal of identity gathering tool, MPSPR, DPI recombinant DNA methods, supposition tool, arithmetical technicalities, nanomechanics, and computational move approach. Bottom-up multi-scale simulation, supercomputing. It takes a village of techniques.
Now let's talk about nanosensors. Eyes and ears at the nanoscale.
You could say that. A nanosensor is an organic element or surgical sensory position worn to communicate information about nanoparticles toward the macroscopic planet, getting signals from the nanoworld out to where we can measure them.
What are the main uses? Medicine. Building blocks.
Primary uses are medicinal reason, and as gateways to construction of other nanoproducts like computer damage, nanorobots. Planned creation methods include top-down lithography, bottom-up congregation, and molecular self-assembly.
What are the predicted applications of nanosensors detecting disease?
Medicinal utilizes a big one.
Right.
Accurately identify demanding chamber or seats in the body. They could gauge modify in volume, attentiveness, dislocation and speed, gravitational, electrical, attractive forces, pressure or warmth of chamber inside remains.
Allowing them to spot specific cells.
Potential to differentiate and distinguish convinced cells, yes. For example, light-responsive nanosensor for local protease activity to notice resistant rejoinder or melanoma. Or they could work externally. Notice macroscopic variation from exterior of the remains and converse these modify to other nanoproducts working inside.
But nature already has existing nanosensors, right?
Absolutely. Most ordinary mass-produced performance nanosensor exist in biological world as natural receptors of exterior inspiration.
Like smell.
Examples.
Mhm.
Sense and stink dogs use receptors to intellect nanosized molecules. Plants identifying sunlight. Fish exercising nanosensor for minuscule atmosphere changes. Bugs detecting sex pheromones. Nature perfected it first.
How are artificial ones made?
Mm.
Manufacture methods. Lithography.
Conjecture habits to produce nanosensor include top-down lithography, starting with larger chunk, stacked you out preferred form. That's how most integrated circuits are made. Application includes exact microelectromechanical system, microsensors, now including nanosized mechanism, also bottom-up assembly.
What about the economic impacts of nanosensors? Is it a big market?
It's a relatively original field globally, but growing. Projections for trade of foodstuffs incorporating them were $2.6 billion to $2.7 billion in the next 3-4 years, a while back, and it's likely grown since.
Where will they be integrated? Computing.
Likely in most contemporary circuitry for advanced computing, providing that supply link between nanotech and the macroscopic world, miniaturizing processor break-off, greatly increasing storage legroom. They're essential interfaces.
And the social impacts of nanosensors, beyond health and environment.
These are harder to describe, maybe harder to predict compared to health ontological impacts. Good or bad isn't always clear.
How could they transform society?
Transformation of societal instruments. Advancement in identifying sensing biological substance species with amplified capacity and exactness may change systems based on uncertainty accurate information. For example, calculating extremely low amounts of air pollutants toxic equipment in water raises questions of risk entrance, especially if technology outpaces public reaction. How clean is clean enough?
What about medical sensors and privacy?
Medical sensors could not only diagnose conduct, but may also forecast future outline of an entity, impacting health cover companies' funding denial of reporting based on future risk, and other issues. Solitude, assault, and security matter from widespread use of nanosensor observation devices. Lots to think about.
Let's revisit nanotoxicology with a bit more detail.
Yes.
Studying nanomaterial toxicity.
Right. Definition. Study of nanomaterial toxicity. Reason for unique toxicity. Quantum size effects. Large outside area to volume relation, as we've discussed. It's a branch of bio-nanoscience dealing with study and application of nanomaterial toxicity.
Even safe materials become reactive.
Potency can change dramatically. Still, basics like gold become extremely energetic at nanometer compass. The purpose is to establish whether properties pose danger to atmosphere or human beings.
Is there much beta?
Example. Diesel nanoparticles have been shown to spoil cardiovascular organization in mouse representation. There's growing evidence.
So nanotoxicity studies are crucial, but there are gaps.
Regulatory gap. No specific right yet to regulate all nanotech-based harvest, though it's evolving. Scientific evidence. Some nanomaterials can be poisonous to person or surroundings.
Like that fish study with fullerenes.
That March 2004 study by Eva Oberdorster at Southern Methodist University was notable. Fish exposed to fullerenes for 48 hours, modest dose 0.5 ppm, showed widespread intelligence harm, changed gene markers in livers, physiology affected, killed water parasites, maritime provisions chain link. It raised alarms.
And they're easily absorbed.
Ease of uptake. Fictitious nanomaterials taken up more willingly by income tissue than known toxins, often due to size. Routes of exposure. Draw in, consumed, wrapped up during skin, intentionally mistakenly injected, accidentally unintentionally released from equipment, entrenched in income tissue. Many ways in.
What are the main challenges of nanovisualization and related unknowns? Hard to see, hard to understand.
Exactly. Lack of simple categorization of contaminants at nanoscale makes it hard to appreciate the risks. Organic systems themselves still not totally known at this scale. Visualization techniques like electron microscopy, atomic force microscopy help, but have limits.
And characterizing them is complex.
Need for precise characterization. Size, substance composition, detailed profile, aggregation level, combination with other vectors, crucial. These properties must be determined not only before introduction to living environment, but also within the mostly aqueous organic situation, which can change them instantly. It's a moving target.
Finally, let's discuss lab on a chip, LOC, miniaturizing the lab.
Right, definition. Device combining one or some laboratory meaning on a private chip, millimeters to few quadrangle centimeters, for mechanization and high-throughput performance.
Handling tiny amounts of liquid.
Exactly. Function. Deals with behavior of extremely little liquid amount, less than picoliters. Connection. Indifference of microelectromechanical system, MEMS campaign, routinely associated with micrototal scrutiny systems, TS.
Related to microfluidics.
Relation to microfluidics. LOC is directly connected to and partly covers microfluidics, physics of fluids at microscale. Distinction, strict. Lab on a chip signifies degree of single manifold lab processes down to chip format. TAS is dedicated to accumulation of entire sequence of lab development for matter analysis.
So LOC is a broader term then.
Origin of term. Lab on a chip, introduced later as TAS technologies, proved more generally applicable beyond just analysis.
What are the advantages of LOCs? Less waste, faster results.
Many advantages. Low liquid volumes utilization, less waste, lower reagents costs, less required sample volumes for diagnostics, quicker scrutiny and answer period, short diffusion distances, fast warmth, high exterior to quantity ratio, little warmth capacities. Recovered process manages, faster answer of the system, thermal control for exothermic chemical reactions.
Smaller, more parallel process.
Compression of systems, mixing much functionality in small volumes. Massive parallelization due to compression, high throughput analysis. Lesser invention costs, cost-effective throwaway chips fabricated in mass making. Part superiority established routinely, safe for display place for chemical, radioactive, natural learning due to incorporation of functionality, less important solution quantity, store energies.
Like a portable genetic testing lab.
Exactly. Example, genetic testing chip. putting complex lab processes onto a small, potentially disposable device.
And there you have it, a truly deep dive into the fascinating landscape of nanotechnology. We've explored everything from its fundamental definitions and intriguing history to the intricate details of nanomaterials and their diverse applications across industries.
We covered quite a bit, from the basic science to the engineering and NEMS and MEMS.
We've also delved into the groundbreaking world of NEMS and MEMS and the transformative potential of nanoelectronics.
And nanomedicine, with its potential to revolutionize how we diagnose and treat diseases at the cellular level, and even how nanotechnology is impacting everyday products, food, and environmental cleanup. It's really touching almost every area.
It's clear that this invisible scale is visibly reshaping our world, offering solutions to some of humanity's greatest challenges in energy, the environment, health, and computation.
It really feels like we're just scratching the surface, too.
As we conclude this deep dive, consider how this journey reveals that the smallest things can indeed have the biggest impact, not just on our technology, but on our fundamental understanding of what's possible.
Yeah, it makes you think. What's next?
What new frontiers of miniaturization and precision do you envision? And what responsibilities come with designing at the atomic scale? This journey into the nano world is truly just beginning for all of us.